Well, welcome to the DBMS Performance and Resource Optimization session. Now, in this session, we're going to be talking about optimizing your SQL statements, optimizing your database in such a way that will help you get access to your information as quickly as possible. That's going to help your application to function in a much snappier way. So I think it's important that we understand these concepts. SQL optimization principles and considerations is primarily what we're going to be talking about in this session. We're going to be talking about standard indexes and how those work. This may be a refresher for a lot of people, but I think a lot of people will gain a lot of insight and understanding as we dig a little bit deeper into how the standard indexes actually work when it comes to accessing your data. We're also going to be looking at table analysis and how table analysis provides the SQL engine with certain information that helps it to best optimize your SQL queries. And then we're going to be looking at full text indexes and how they differ from your standard indexes and how they provide lightning fast access to your data in a little bit different way that standard indexes just can't do. In particular, that's going to be character-based or long text data. So we'll be looking at how those work. And then we're going to be looking at some real-world examples of how we can improve and understand the performance of certain queries in our database. All right, so let's start off first by talking a little bit about the structure of the SQL engine, what it is exactly. So this is the heart of the BBJ DBMS. That is the SQL engine which provides access to your data through the use of the SQL language. So if you look at this diagram over here, you can see at the bottom that we have BBX data files at the lowest level, and the BBX data files contains all of your data. Those are the files that you might read from and write to from your BBX applications using read record, write record, read, write, remove, those kinds of operations. And those, as you're aware, you send kind of raw byte data to that data file. So in order for SQL to work, it needs to know how to interpret those records that are stored there in that byte array format. So that's where the data dictionary comes in. The data dictionary contains information necessary to understand and parse that data that's contained in those records so that it can return it as column values, for example. So it knows how to extract from a customer table the customer number, the first name, the last name, and so forth. The SQL language then sits atop that, and it uses the information that the data dictionary provides to understand how to execute SQL statements. So not only is it an SQL parser that understands the SQL language, but it also will be interacting with the data dictionary in order to understand what the data looks like, and then how to access that data in a way that is meaningful and that is accurate according to the query that it's submitted. And then, of course, at the very top there, you see how the BBJ interpreter can talk to the SQL engine, and the JDBC driver and ODBC driver, those both will interact with the SQL engine through the appropriate API, and that allows access to third-party applications so that they can access your BBX data using SQL. And those would be things like Microsoft Access and Excel, a SQL Server, reporting tools, and those kinds of things. All right, so when it comes to the SQL engine, the file system, as I said, provides access to the data files. It also includes trigger definitions. So if you're not familiar with triggers, these are really cool. This is a way that you can execute BBJ code in response to certain operations that occur on a data file. For example, if you have a before write trigger, then before the write occurs, you can execute BBJ code to process that data further or to respond to it in some way. The same with a read operation, and after read, it would respond after the read occurs, that kind of thing. Now, we're not going to go into details on that, but that is a cool feature of the file system, and it's also accessible from SQL. The data dictionary defines database entities, and those would be things like tables, views. A view is basically an SQL statement that is executed, and the results of that statement can be conceptualized as a virtual table. It also contains stored procedures and sequences. So those are considered database entities that the data dictionary defines and stores and provides access to via SQL. All right, let's talk now a little bit about optimization, since that's what this session is primarily about. So optimization applies to tables in the BBJ DBMS and views by extension. Since views access tables, then it would apply also to views in a sort of indirect way. At the core, it works in the same way as optimization using read, with a knum equal and a key equal. So if you have read statements and you're familiar with that, and you're familiar with using a knum equal and a key equal, essentially the optimization in the SQL engine works in that same way. In fact, at the lowest level, it's actually passing in a key number and a key equal value when it's doing its optimization. Basically, what you're doing in this case is you're specifying a jump value so that you can skip records that you know have no chance of matching the query results requested. With SQL, the engine actually intelligently decides which key and which value to use. So that's what the optimization strategy is going to be trying to accomplish. Its main purpose is to say, what key number should I iterate over, and what key equal value or jump value should I use in order to get the best possible performance. Now, a good way to understand this is to look at some examples, and that's what we'll be doing now. So in this example here, we have a data file with no index on it. So this contains a make of a variety of different cars. So this will be a car table, for example. And we're looking at just the make column of that car table. So as you can see here, we have a number of different makes. And let's say that we want to execute an SQL statement that says where the make equal Nissan. In this case, there is no index, so we can't do any optimization. And here's what happens in that case. As you see, we then have to iterate over every single record in the file to make sure we don't miss anything important. So we read the first one, we read the second one, we keep iterating over it, and nope, that's not a match. Oh, we found a match, Nissan, but we aren't sure if that's the only one. There might be another Nissan, who knows? We have no way of knowing, so we have to keep reading. And then we hit the end of the file, and since we're at the end of the file, we obviously know there's no more data, so we go ahead and stop. So in this example, there's seven records there, not a big deal. But if there were 7 million, that would be a problem. That would take a long time to iterate over that. And that's what's necessary to return the one matching record from that query. All right, so when we start off talking about optimization, the first thing that we need to understand is index order. So when it comes to index order, this kind of is at the foundation of this ability to optimize our queries and to use these keys and indexes. So the ability to optimize an SQL statement requires the presence of an index, as I pointed out a moment ago, or in file system terms, that would be a key. Optimization relies on BBJ's ability to read as few records as possible in order to return those results. That's the whole purpose of optimization. Do as little work as possible when it comes to iterating over the data file. All the values in the key and the index have to be ordered in order for this process to work. We'll look at that a little bit here in just a moment to clarify what I mean by that. BBJ must be able to jump to a position in the key in order to, again, skip over records it knows it won't possibly meet the criteria. And ordering means BBJ is certain it can stop reading. So these indexes are, the values in those indexes are ordered. That ensures that we're able to jump to a particular point, knowing that we didn't accidentally miss anything. It also ensures that we can stop reading when we hit a certain point, knowing that we didn't stop too early by accident. Now, the easiest way to understand this is to just look at our same example again, now with an index. So we have our same list of makes from the car table. And in this case, again, we're going to be saying where the make equal Nissan. So we have an index on the make column here. And so what we're going to be doing now is we're able to jump right to the one matching value. Notice they are in alphabetical order. So we know that jumping to the first instance of Nissan, we know that Lamborghini, Ferrari, Chevy, Alfa Romeo, those all come before. So we know that they couldn't possibly match our criteria here because they sort prior to Nissan. The same is true after that. We know that there's nothing after that either, so we don't have to read any additional records, and that one read then returns us our results. All right, let's look at another example that's using an index here. So in our previous example, we used a simple equal, right? We said where the make equal Nissan. In this case, we're going to say where the make is like a value that starts with F. So with the like statement, if that's new to you, the letter F at the beginning means it starts with F. The percent means F followed by 0 or more characters. So it's kind of like a wildcard character. Or the equivalent would be something like make is greater than or equal to F and make is less than G. So both of those mean essentially the same thing. Now, in this case, we still have that index on the make column. And you'll see here that we can't jump immediately to an equal or to a single record because it's not an equal. We're using a range of values here. But what we can do is we can say, well, we know it starts with F, so let's go ahead and just jump to the Fs. So we immediately jump to the Fs, and as you can see, we skipped over those records. And again, this is emphasizing the importance of the sort order here. If this was not sorted, we would have no way of knowing if we could jump to that portion of the file. But as you can see, we jump to the first F, we read it, it's an F. We read the next one, it's also an F, it matches, good deal. We read one more and we discover, oh, it's greater than G, it's greater than F, it's outside the range. So we know that every other value after that is also going to be outside the range, so we can stop reading there. So with those 3 reads, we're able to return 2 records. Now, again, we have 7 records in here, so we only really skipped over 4 of them. But if this was 7 million records, keep in mind that it would return these 2 records in the same amount of time as it did in a 7-record table, because it's able to skip over all of those millions of records prior to it and all the millions of records after the fact as well. All right, so now the next thing we want to talk about is string templates. So keep in mind what I'm doing here is I'm setting a foundation of understanding of the various components of optimization so that we can then use that understanding of those fundamentals when it comes to building our own queries. So now when it comes to string templates parse byte arrays and return readable values. So again, the data files at the file system level essentially store byte arrays. And a string template allows us to quickly and easily parse that byte array into meaningful fields like customer number, last name, first name, those kinds of things. And it handles strings, binary data, as well as numbers. Each template field type is going to be stored in a different format, and that's important to understand. Some of these formats sort so that the readable values sort the same as the raw bytes. Now, this hopefully is now making you understand why I was talking about sort order and why we started at that when it comes to optimization, because only these types of fields can be used for optimization when they're present in an index. So if we have a data type that does not sort properly, then the SQL engine is going to say, oh, it's this type of data, therefore I can't use it because I can't guarantee that it's going to sort correctly. Now, you may know that it sorts correctly, but we don't know that. We have no way of knowing that. The SQL engine doesn't know that your data just happens to be sorted properly. And so in order to make sure that we don't return incorrect results, we just say, nope, can't use that for optimization. That can become a problem, obviously, especially if you think that it should provide that optimization for you. All right, so now we're ready to look at these value types. So again, that sort order is so important, but let's talk about how these different value types work and how they impact that sort order. All right, so let's just start off with character-based columns. Those are actually the most common, which is great because typically they sort really well. And so since most people tend to use a lot of character data in their BBX data files, then this is good. So with character-based columns, they sort alphabetical-ish. And I say ish because the default is ASCII byte order for the sorting, which means the letter A, a capital letter A, is going to be 65, B is 66, C is 67, and so on. But lowercase a starts at 97, and lowercase b is 98, and so forth. So you can see how the lowercase a is actually going to sort after the uppercase B, which, from a language perspective, that's not correct. This is a good reason why a lot of times in older software, especially, that people would uppercase all the data so that there was no mixed case involved, and it made it much easier to look up your queries and your searches and find data that you were interested in. That way you didn't have to worry about the case. Now, however, BBJ did add case-insensitive keys in some later versions of BBJ, and this mitigates that issue. And these sort alphabetically regardless of the case. And so, as you can see, that makes that much nicer if you want to, or if you prefer to store mixed case values in your database. Now, when it comes to binary data, just assume this doesn't sort properly. BBJ's SQL engine is going to ignore that. Now, one thing I do want to point out with character-based columns is the whole purpose of understanding these value types is to understand why the BBJ SQL optimization engine may ignore certain index segments. When it comes to character-based columns, we assume that it's going to sort properly. What that means is that you can get incorrect data results if you are not aware of this case difference here. And so keep that in mind when you are submitting your queries and that kind of thing, that if you're not using case-insensitive keys, then the case does need to match it up for optimization purposes. All right, let's move on to the next value type, and that is numeric columns. So when we talk about numeric columns, there are a variety of different formats for storing number data in string templates. So one common one is type B, or business math. And this type, the raw bytes and the readable values, the human readable value of that number, sort the same, which is great. That's exactly what we need in order to use it for optimization. In fact, that's why the business math type was created and why the format is the way that it is, so that they do sort properly, making them indexable. Now, integer values, or type I, these are an interesting one. Positive numbers sort properly, but negative numbers don't, due to the byte representation in the data file. And so this is an important distinction here. Keep that in mind when you are using type I. So if all the numbers, if you know they're all positive, you're fine. But if negative numbers are in there, then it's going to be a problem. Other numeric types may not sort properly. So those are the two that we know do, but the other ones may not. All right, and as you may be aware, there are other numeric types available in string templates other than business math and integer. There is the type in, which is a really common type used for storing numbers. And interestingly enough, these are stored in your data file as a string. And because of that, they are also stored in the key as a string. So the number 125.25 is going to be stored as a string 125.25. And if you recall, when I was talking about character data being stored in a key, and in the order that that key is sorted is ASCII byte order, you can maybe start to imagine how this could be a problem for type in values. Keys sort according to the ASCII byte values in the same way as strings. So you have things like the number 1 will be 48, the number 2 will be 49, and so forth. The number 125.25 is going to sort ahead of the number 2. And obviously that's a problem. 2 is not greater than 125.25, just in case you needed a little math refresher there. So that's going to be a problem, right? So BBJ sees that index and says, well, I can't really use it except for equality. I can immediately jump to a value, but I can't skip over values and iterate because I have no idea whether the values I skip over before or after are going to be valid or not. However, BBJ did add the ordered numeric flag for keys, and this mitigates this problem. So you can look at, if you're interested in making this change in your application, you can look at the X-keyed verb, V-keyed, M-keyed, all those verbs. They now allow you to specify an ordered numeric flag for numeric type data, and then that will allow it to sort properly, and then you can use it for optimization purposes. Keep in mind that it's not just a matter of switching out the file type underneath. If you have read operations that use a knum equal and one of those numeric values, you'll have to do some changes. We won't go into that here in this session. That's kind of beyond the scope of this, but just keep that in mind. The documentation will tell you what you need to do there. The SQL engine, though, it can handle it automatically for you, so you don't need to worry about that. But at the SQL engine level, you can go into the Enterprise Manager and you can put a little check mark in the ordered flag for your numeric column segments if you would like them to be ordered instead of the standard unordered segment order. All right, so why did we bother discussing these details? Well, that's because I think it's really important when you understand something at the root, when you understand how something works, you're much more likely to be able to get the most out of that. Whether it's software like we're seeing here, whether it's a power tool that you have in your garage at home, whether it is another human being. When you understand what's going on in their head, you can better understand how to interact with them. All of those kinds of things. I always think that it's really helpful when you can understand how things work to really get the most out of it. So let's kind of summarize a little bit of what we talked about here so far. So most queries where an index is present can optimize on equality comparisons. So keep in mind that equality comparisons don't really rely on the sort order. They can jump to a particular key value in a index. Now that's going to be the case for primary key values where we know there's only one match. But in the case where there's more than one, we do have to iterate over all of the records in the file. So just keep that in mind that sometimes we can optimize certain kinds of queries if an index is present, but not always. And that, again, that's going to come back to the data type. Now, the exception to this, though, is when the key is case sensitive and the values presented are not in the matching case. So, you go to look up the value ABC in all caps, but it's stored in the database as all lowercase ABC. It's not going to find that value because ABC in all uppercase does not match lowercase ABC at the key level. So it's going to be unable to find that. So keep that in mind also. Many inequality queries cannot be optimized based on the underlying data. And hopefully you understand why now. And that's because of that sort order. And then, of course, the result of this is that your queries are potentially going to be much slower, if not even unusable. So it's important that we understand this when we're thinking about the data types and the data that we're storing. All right, so now we've talked about those data types that are string template types, like character, type C, in, type B for business math, and so forth. When we understand how those sort and maybe don't sort. Date values are kind of a special case, though, and so we do need to address these separately. And the underlying data must not only sort, but the ASCII byte array order must match the date sort order, which is another whole layer of complexity there. The part of the reason I say that's complex is that not everybody who creates BBX applications stores their data in the same format. There are numerous date formats out there. Some data files actually have multiple date formats inside the data file. The original developer used one that was a 3-byte packed date value. Later developers added an additional date column, but they thought, hey, this would be better if it was a nice plain string representation, which makes sense. But again, you have multiple date formats. And so when you start indexing these tables to improve your performance, you can see how you would run into some issues there. Dates stored as a string, for example, 10/13/2022, that would be October 13th, 2022, that won't sort properly. And we'll see why in a moment. Date stored as 2022, 10/13 will sort properly. So as an example here, you can see 10/13/2022 and 11/13/1971. 1971 should not be sorting after 2022, but because the month is at the beginning, it messed up that sort order. Whereas if you change the order of the year, month, day in the date value, that it will sort properly if you have the year first and then month and then day. So BBJ doesn't know if your date format will sort properly. So you must explicitly tell BBJ that it does. And BBJ takes your word for it. So what you want to do is go into the database settings, and there's an optimized date column setting there. If you know that your date format sorts properly, then just put a little check mark in there, and then BBJ will use that for optimization. This is a good thing to check if you are experiencing slowness when looking up date values. It may be that all you need to do is come in here and put a little check mark there and make that change at the database level. All right, now we know how optimization works. We understand the inner workings, right? We are all experts on understanding the optimizations inside the SQL engine. But how does the SQL engine know which key or index to use if multiple options are available? Now, this is a great question because this is extremely common. to have a where clause that says where some column equals something and another column equals something else, or this column equal that, or that column equal this, and this complicated where clause passing in all this filtering criteria. The SQL engine ideally should be able to look at all of that and say, okay, well, this index would give me a much better performance if I use that one rather than this one. So how does it do that? It's magic. Well, no, actually, it's not magic. It's something called table analysis. And this gathers statistics about the uniqueness of values given a combination of index segments that are based on the where clause. So it tells us information like, is the city column more unique than state? Well, we probably know that, right? We know that, yeah, of course, city is more unique than state, but the SQL engine has no way of knowing that without having looked at every single record in the data file to know that. So it would have to look at that, and you don't want it to do that every time you execute a query. That wouldn't make any sense. That would take way too much time. Is a state column more unique than last name? Well, again, we know as human beings that last name's probably more unique, but again, the SQL engine doesn't know that. If I provide one value for a 3-segment index or 2 values for a different 3-segment index, which will require fewer file read operations. So these are all questions that the optimization engine needs to be able to answer in order to actually choose the best index to iterate over. It can guess, but we really want it to actually make the most accurate estimate. Now, when it comes to table analysis, keep in mind that table analysis may take a very long time to complete because it has to read all of the data in your data file in order to generate these statistics. But the good news is it only needs to be run one time or when a significant change occurs in the makeup of your data. So if it hasn't ever been run, obviously it would need to be run at least once. But beyond that, the only times that you really need to run it again are if your table grows significantly larger. And by that, I mean, I don't just mean it grew from 1 million records to 1.1 million. I mean, that's not really that significant. It's probably still a very similar makeup. But if it grows from 1,000 records to 1 million or 100,000 records to 1 million, you probably want to run it again because it's grown enough that the makeup of the data could have changed significantly and impacting optimization decisions that the SQL engine would make. If a new index is added, you definitely want to run it again so that new index can be factored into the equation. Because if you don't run it again, then that new index will be ignored by the optimization strategies. Or a significant change in the uniqueness of values occurs. Something like this would be if you used to operate in a single state, now you're in all 50 states. Well, now the makeup of the state column is going to be different, right? It used to be that every value was New Mexico, and now there's 50 different values in there. And so it's no longer just a single value, which means it's actually more useful in optimization. Now, here's in the Enterprise Manager where you can find out this information about table analysis. So as you'll see here, we have 3 things highlighted. We have the legend up at the top, and it shows the icon that indicates that a table has been successfully analyzed, and that's what that green check mark is. You'll notice here that under last analysis, it says no info available. That means that the table has not been analyzed. So if you go back to your office and pull up your database and all of your tables say no info available, this is why your queries are running slow. So make sure to run table analysis before you do anything else. Notice too in the status column that you have the ability to see which tables have been analyzed, or if there's some info available or a warning of some kind or that kind of thing too. So that legend up at the top there will tell you what those various icons mean. Now you'll notice once you have run table analysis that you'll see that little green check mark there next to them. You'll also see the last time table analysis was run, if there's info available. You do see that there are a couple of tables there that say no info available. You may be saying, well, why is that? Well, look at the number of rows there. They are 0. So there's no data to analyze. And so in that case, we're going to leave it as no info available. If you start adding records in there, then you're going to want to run table analysis to make sure that it generates some information for you there. So keep that in mind. If you see anywhere there are no records and then suddenly there are, table analysis will need to be run again. All right, so up to this point, we've been talking about standard SQL indexes. And standard SQL indexes are great for optimizing your queries, and every SQL engine out there is going to have some form of index like this. Now, the problem is that they aren't suited for every kind of query. So there are a number of queries, especially when we're dealing with text, that these standard indexes just have a number of limitations, so many limitations, in fact, that there are a number of queries that cannot be optimized. And we'll look at how that works here in a moment. But this is where full text indexes come in. And not every SQL relational database supports full text indexes, but we do, which is great. So they differ from a standard index significantly. In one big difference is that they're built using Lucene technology. Lucene is a best-in-class full text search engine. It's much like Google, how Google would index a text document and then give you the ability to quickly locate those documents with just a few words, and you can use search phrases and that kind of thing. And Lucene supports that same kind of search capability over your SQL data, which is great. It's not part of the data file, but it's kept in sync with it. And this is an important thing to understand. You don't have to recreate the data file and copy the records into it like you would if you were going to add a new standard index or new key to your data file. In this case, it runs alongside the data file, which also means that you don't run the risk of making a change to the data file while people are trying to use it and causing problems there. You don't even have to wait for people to quit using the system to create one of these full text indexes. It can run right alongside it, which is a nice feature as well. And it provides lightning fast lookups for things like much more complex searches. You can search within large text columns. You can search multiple columns simultaneously. So you could search the first name, last name, company, and city all at the same time with one search phrase, which is kind of cool, I think. You can also search a table and its related tables. And if you're using the enhanced data dictionary, which supports foreign keys, or if you're using ESQL files. And what I mean by that is you can search the master table and then the detail table all at the same time with a single search query, which is kind of cool as well. All right, so full text indexes help when these traditional indexes would be suboptimal or of no use at all. When searching for sequences in the middle of strings, this is one of the limitations of standard indexes. When you're searching for sequences in the middle of strings, the value must appear at the beginning of the string to be used for optimization. And that's a significant limiting factor. For example, find the word chili in the string green chili stuff, right? Well, a traditional index would require a like statement like this. So like %chili %. And you may not realize at first that can't be optimized because there is a wildcard character at the beginning of that string. So we can't use that as a lookup value for keys in a standard index. And however, full text indexes do allow you to do that. And they allow you to search all or some columns for a value. For example, you can search for John in the first and last name columns. The segment order doesn't matter as it does for standard indexes as well. So with standard indexes, the index with last name, comma, first name in that particular order, if you specify only a first name, we can't optimize on that. And that's because there was no last name put in because last name was first. Now, if you had specified a last name, then you would be able to use that for optimization. So you can start to see some of these limitations here. Now, when it comes to complex searches for full text indexes, you can use wildcards, and that can appear anywhere in the string. And we can still optimize it just as quickly. You can also use proximity searches, so characters within a certain number of characters of another character. Kind of an odd case, but there are some significant use cases for that for many people. Fuzzy searches, where where your search is, I'm looking for something sort of like this. So that's kind of a cool feature. Range searches, you can look for that. And all of those things can be optimized extremely fast. So the other thing to understand too that with all of these different complex search capabilities, it does not slow down the lookups at all. So you get these lightning fast searches just as if you were using standard indexes. And the results can be joined with traditional lookups, which is another powerful feature of this. So you're not limited to just using that index, but you can actually then join the results of that with the additional features of your SQL queries. All right, now for the good stuff. So now we are done with all the theory and all of the understanding of the inner workings. Now we're ready to look at some real world examples and kind of put what we've learned to good use. All right, so in our first real world example, how can we improve performance when a query provides a filter criteria that does not provide a value for the first segment of an index? So if you recall, I pointed out that if you don't provide a value for the first segment of the index, you can't use it for optimization. How do we get around that? How would we resolve that issue? So that's a very common scenario. And as you can imagine, I'm looking for last name. Okay, this time I'm looking for first name. Cool. This time I'm looking for last name and first name. Okay, well, now this time I'm looking for first name and company, but I don't care about the last name. Or I'm looking for company and city, but I don't care about the name. So how do we index things so that we can get back these results as instantaneously as possible? So let's go ahead and look at this example. All right, so let's take a look at this very simple example, and hopefully this will help you make sense of how the optimization works. And this should extrapolate nicely to much more complex scenarios. So in this case, we're going to be looking at very simple queries here where they reference a single column in the where clause. But before we do that, let's take a look at the table we're going to be working with. So the customer table here has some indexes defined. It has one on custom, that's our primary key. And as you can see, it only has a single segment defined. However, the last name index here does have a segment for last name and state. So in our mind, intuitively, we may look at that and say, oh, okay, well, this index should be able to be used for optimization purposes whenever I'm referencing the last name or the state. And that's sort of right, but not quite. So let's take a look at it. So when we come over and look at a couple of SQL examples here, the first one here is select star from customer where last name equals Baldrake. So we look at that and we say, okay, well, it is referencing the last name column. And coming over and looking at our table definition, it does have an index with a segment on the last name column. So it should be able to use that for optimization. And that's actually a correct assessment. It can use that. It can provide the last name, fill in the value, and then the file system underneath the SQL engine can jump to that particular key in the file, iterate, and it knows when to stop. And so it can skip over all the records that are not a really close match to that. So that's great. That's exactly what we want. That's what optimization is trying to accomplish. Help us to look at as few records as possible. But if we come over and look at this particular query, select star from customer where state equals New Mexico, we may say, oh, well, yeah, state is referenced in this particular index, so it should be able to use that for optimization as well. That's actually incorrect. So the reason for that is that we need to be able to fill in all the values prior to the value that we are trying to optimize on. So if we had a last name and a state specified, well, then we could fill in the last name and fill in the state and then use that for optimization. However, in this case, we only have state. So it doesn't have a value that it can fill in for last name, which means it has to stop there. It can't go any further once it has reached a column that it doesn't have a value for, or a segment that it doesn't have a value for. And that means that of these two segments that make up this index, none of them are usable, which means then that this index is not usable. So how would we go about resolving that? Well, what we could do is, well, we could reorder these segments, but then we have the same problem if we tried to look something up by last name. Or we can just add a new index. So we add a new index and we add a segment for the state. So we find our state column, we add that in, and now since state is the only segment in there, when we include a where clause that's looking for a particular state, it can use that for optimization purposes. Now, again, we could put multiple segments in there. Let's say that we typically search on state and city. Well, we could put city in here as well. And that way, whenever we included city and state together in a where clause, it would be able to utilize that index for optimization purposes. However, we run into the same issue if we only search for city and don't provide a state. So that should help you when you are trying to optimize a query. Just remember that you need to have a value for any index segments that are present prior to the one that you are interested in. And if you don't, then it can't use that for optimization. All right, we're ready to move on to real world example number 2. So in this one, this is actually a question that was asked by a developer to our support department, and then it was passed along to me. And so this was a really good question. I think it's probably a relatively common question. How can I estimate the amount of time it will take to execute a query? So yeah, you could execute the query, but in other words, this query takes a long time to complete. Is this expected? And I think that's probably more accurate as far as the question we would really be asking. It's like, yes, I want to estimate it, but really what I want to know is, hey, is this query running as fast as I think it should be, or am I missing something here? So let's look at this example and see how we might be able to come up with a good answer for this. All right, so let's come on over to the Enterprise Manager and take a look at this particular scenario. Now, I will say this, that we can't really help you estimate the exact amount of time that a query would take to execute. So we can't give you the number of minutes, the number of seconds, the number of hours, that kind of thing. What we're talking about here is helping you to be able to take a look at the information present in a query and say, this query should run pretty quickly, or this query is probably going to take a long time to run. That kind of thing. So it's not very precise, but it still can be somewhat helpful. So we're going to be taking a look here at a very small table just for our example purposes here. And this is in the Chili Company database, the customer table. So in the customer table, we have a number of indexes present. I've modified these a little bit for our example here, and I've added a couple of additional ones. But you can see here we have an index on last name, one on city, state, country. We also have one on a combination of the last name and the state, and another one on the combination of country and last name. So now let's go take a look at how we might use this information here. So what I've done is I've created a get_scores stored procedure that's going to process the table analysis data for us in a way that might be a little bit more useful for us. Now, we're not going to go over what's in this stored procedure. I will be making the source code available so that you can add this to your database if you would like. And at some point, we're going to add it into the BBJ product. It'll be a built-in stored procedure. But for now, just understand, let's just focus on what this stored procedure is returning to us. So we look at the get scores call here on the customer table and the last name. So you may be saying, well, what does that mean? This would be assuming that we are querying the customer table and we're providing a last name value. So that's what this means here. So this first value is the table you're interested in. The second one is the list of columns that you will be providing information for in your where clause. So as you can see here, we have last name and country. We'll be looking at that one here shortly. So in our first example, we execute that query and it pulls up and says that the last name index, key number 1, would give us a score of 1. Now, what this is telling you is what the internal SQL engine optimizer is going to be doing in determining scores when it's choosing how to optimize your SQL query. So what this score of 1 means is that on average, when you provide a value for the last name, it's going to have to read one record from the data file in order to find all of the results that will be returned to you. So in this case, what that score of 1 tells us is that the last name column is pretty unique. And I do know in the customer table in the Chili Company database that there are no duplicate last names used for customers. But in your particular customer database, for example, your customer table, it's likely that last name would not be completely unique. And so this score would actually be higher. But it also tells you the percentage of the records that makes up. So in this case, that's 1.47% of the records. Now you can also see it also has a match for the last name and state combination. But again, last name is the first segment. And so it tells us the key number here. And again, if we only provide the last name, it's still only going to have to look at one record in this case. Now, again, in your database, it may be that adding the the last name and state together would be even more unique than just the last name. But hopefully that's clear there. Now let's take a look here at the custom or the country. So if we provided a country value, we provide a country value here, then you can see here it found a matching key that it could use for optimization purposes, and key number 4. The score is 5. What that means is country is less unique than that last name column that we looked at a minute ago. And so if we were to provide the country in a where clause, then it would on average have to read 5 records to return us all of the matching results from a where clause that had country equals some particular value. So what this tells you here, hopefully this is starting to make a little bit of sense here. What this is telling you is that you're able to take a look at the tables that you would be including in a query, and you can look and see what information is available to the optimization engine within the SQL engine for optimizing those queries. And you can take a look and make some estimations here on how long this might take. So in our case here, we look at this and it says, oh, it's only going to have to return or read 5 different records in order to return my values. I can assume that's going to be very quick. Now, if this said 500,000 or 2 million, well, then that might be a problem, because then what that means is it's going to have to read that many records in order to return my matching data. That could take a long time. And so at that point, then I may want to go and see if there's anything I can do with my indexing to better optimize it so that the optimization engine in the SQL engine has some additional information that it can use, additional indexes at its disposal in order to make those queries perform better. And then finally, this last example here uses last name and country. We execute that, and you notice it has 4 different matches. So it says it could use the last name column, where it would be providing 1 segment because the last name will work in there. And again, it gives us a score. The country, it could use the country one because we did provide country. Even though last name's not included in that country index, it could still use it because we provided information to make that usable. And you can see that the score there would be 5. Now here, last name and state together. Last name, again, is part of that one, and so it could use it. And country and last name combination together, it could also use that. But because the last name column is so unique, if it were to choose this one over country, you would see it's going to be a lower score and potentially a quicker query. Now, looking at this, the reason that I put this in here is not only can this help you make some of these estimations on your own, but it also helps you to understand what is going on inside of the SQL engine when it's trying to optimize queries. So what the SQL engine is doing is essentially gathering the same information, all kinds of different permutations of how it could use the various indexes that are at its disposal, and it finds which score is going to be the lowest, and then it uses those indexes in order to optimize the query. So again, if all these numbers are really high, when you start to run this get scores stored procedure against the various tables that are going to be included in your query, then you may want to go in and take a look at what indexes are available, or even maybe look at possibly incorporating a full text index, which may improve your performance as well. All right, and we're ready for real world example number 3. So in this example, I need to generate a complex result set from multiple tables using a combination of full text index searches and standard SQL where clause filtering. And I need to do this using a single SQL select statement. So obviously that's somewhat of an arbitrary limitation maybe, but it may be that you have a report where you truly do need a single SQL statement to gather the data that's necessary. And so let's take a look at how we might be able to accomplish this as well. All right, so we're back over in the Enterprise Manager, and let's take a look at how we might accomplish this. So to keep things simple, we'll start off with a very simple example here. As you'll notice, we have a call statement here making a call to a built-in BBJ stored procedure that will utilize the full text index. Now, this particular procedure, BBJ underscore search underscore table, will execute this search looking for the word chili in the item table, and then it's going to return to us a result set that contains the complete record from the item table. So not just the columns present in the full text index like the BBJ_index stored procedure would do. This returns the entire record for us. So it's a much quicker way of getting all of the information from the table. Now you'll notice here that I wrapped it in parens at the beginning and end here, and then I added a select star from in front of that. What you're able to do is treat the results of this call statement as if it were a virtual table. And that's going to be important as we go take a look at the next examples here. So we say select star from the results of this call statement. We execute that, and as you can see, it returns us a list of all the records that have chili in the description somewhere. So chili could be at the beginning, the end, in the middle of it, could be part of a word, and it will locate it in there. All right, so now let's take a look at another example where we utilize this in a little bit more detail. So now we're going to say select star from a table, a real table, the order line table, and we're going to say where the item num from the order line is in the results of this select statement here from the item table. Okay, so now again, we're using this as sort of a virtual table, and we're saying, hey, we want all of the order lines where the item number is in that result set. Now, as we execute that, you'll notice something here. It takes a couple of seconds to execute, and that may not seem like a big deal, but these aren't particularly large tables. So it took 2.7 seconds, as you can see there, or 2,700 milliseconds. But we can speed that up. And the reason for that is that whenever you use an in clause like this and a nested select statement, it's going to be executing this nested select statement multiple times. And that's in case you specified some other criteria from this outer select statement within this statement. So it needs to execute it to make sure it's going to give you the correct results back. But in our case, we don't need to do that. We have another way that we can do it that will give us better performance, and that would be to use an inner join. So anytime that you can bypass an in or an exists type of a statement by using an inner join or an outer join, that will probably give you better performance. So in this case, as you'll see, it gives us significantly better performance. But again, the order line, we do an inner join with this result set here, and then we join it on the item num column. Now, as we execute that statement, you'll see it came back really quickly in 6 milliseconds, so significantly faster. And that would, of course, be exponentially slower as the table got larger as well. So as you can see here, if this was a multi-million record table, we would definitely want that increased performance. And something else that we can take a look at now is a little bit more complexity added to that particular query. So we have now an example here where we're going to join the order header table with these results as well. So now we're going to be returning the list of orders, not just the order lines. So the list of orders where the order has an order line in it somewhere that contains an item that has green chili in it. So this will give us a list of all of the orders that ordered something related to green chili. So as we execute that, you can see the nice result set comes back with all of the records from the order table. Now, something else to keep in mind here is that let's say you looked at this and you thought, oh, well, that's really useful information, but it would sure be nice if I could sort that information in a better way. So can we do that? Well, yes, because when we're making calls to a nested stored procedure like we are here and wrapping it in those parentheses, we're treating it as if it's just another table. So we can incorporate things like an order by, and we can say order by order date. And then now you'll notice when we execute this query, if you take a quick look here, you'll see it's not ordered by date. So now we'll execute that query again, and now it is ordered by date, as you can see here. So the main point in this is to keep in mind that you can make these queries arbitrarily complex, joining information from those very fast full text index search results with data in other tables very easily in the way that I've shown you here. All right, and we've hit the end of this session. So in summary, we talked about the SQL optimization principles and considerations to really help you get a good understanding of how indexes work, those standard indexes, how the optimization engine uses those and when it can and can't use them, table analysis and how it provides those statistics that are really helpful for the SQL engine to use to optimize your queries, to choose the best index to use for iteration and those kinds of things. And then also how to incorporate full text indexes to further improve and expand on the searching capabilities that you provide for your end users. And then finally, we looked at those real world examples that hopefully tied it all together and really gave you some inspiration on maybe ways that you can improve your own queries and thereby, improving your overall user experience.